Here in this video, we're going to look at what's called implicit differentiation. Up to this point, when we were taking the derivative of an equation, they have been solved for y. And in this case, the implicit form, notice here we have xy equals 1. This is where the equation is not solved for y. So what we have been doing, if the equation wasn't solved for y, we could rewrite this as the explicit form, and we could simply divide both sides by x, so we get 1 over x, and we could rewrite this as x to the negative 1, and we could easily take the derivative using the power rule, and we would have negative x to the negative second power, or we could write this as simply negative 1 over x squared. So this is what we've been doing up to this point with this explicit form where the equation is already solved for y. Now, what we want to look at here is the implicit form. We want to be able to take the derivative of the function here without solving for y. Now, you may ask, it's pretty easy to solve for y, so why do we want to take it in this form? Well, there may be an equation that is difficult to solve for y, or if we do solve it for y, maybe it's going to make the equation more difficult to take the derivative. So we're going to look at some examples where we want to take the derivative here in this implicit form. To understand how to find dy dx, and remember this is the derivative of y with respect to x, you must realize this is taking place with respect to x. So here I've stressed this before in previous videos that we're taking the derivative of this dy dx with respect to x. Well, what this means is when you differentiate terms involving x, and they only contain x, then you're just going to differentiate just as you've always been doing. Now, when you differentiate terms involving y, we must apply the chain rule, because you're assuming that y is defined implicitly as a differentiable function of x. So here we're looking at y as being some function of x. So if y is representing a function of x, that means we're going to have to apply this chain rule. So I know this makes it a little strange at first, but if you look at some examples, and then if you come back and read through this, I think that will help you understand the idea of this implicit differentiation. If we look at this first example, we have y equals 4x cubed. Well, this is explicit form. The equation is solved for y, and the directions here say find dy dx. So that means we want to take the derivative of y with respect to x. So that tells us here the dx, this is what we're taking the derivative with respect to. So if we're looking for the derivative here, y prime, or another way we could write this, we could write this as dy dx, and this is our variable. So when we take the derivative of 4x cubed, the x here matches up with our variable. So therefore, when we take the derivative, it is simply 3 times 4 is 12x squared. Okay? Now, I do want to point out notation-wise, as a reminder, this equation, y equals 4x cubed, that's just the equation. If the directions are not here to say find dy dx, we don't know what to do with this. All we have is the equation, y equals 4x cubed. Now, if I write the problem this way, as d over dx, 4x cubed, now do I need the directions that say find dy dx? No, because this is actually saying we want to take the derivative of 4x cubed with respect to x. So here, this is saying take the derivative, what's in the brackets, and the dx says we're taking the derivative with respect to the variable x. So here, our x's matches up. So once again, you would simply have 12x squared for our derivative. Okay, so far, here all we have is one variable x. Now, what happens if we have, let's say, d dx of, let's say, x squared plus y squared. Well, this says we want to take the derivative of x squared plus y squared, and we're taking it with respect to x. So the first term that we have is x squared. So we can simply take the derivative as usual. X squared would become simply 2x. But now we have y squared. This variable doesn't match up with our x. So when we take the derivative, we're going to have to use the chain rule. And the derivative here with the chain rule says we're going to take the derivative of the outside function, which would be the 2. So that would be 2 times y. The y is really the inside function. And remember, this y here is defined as a function of x. So we don't really know what this is, but we can simply indicate that by saying we need to multiply this by the derivative of whatever y is. So we could simply write this as dy dx, okay? But we remember that dy dx, to make this a little bit easier here, dy dx we're going to say is the same thing as y prime. So down here, instead of writing dy dx, I'm going to simply say y prime. Now again, that was using the chain rule. For example, if we had the problem, let's say something like 3x squared plus 4 squared. Now, if we wanted to find the derivative here, we would have to use the chain rule. We'd have to take the derivative of the outside, which is the square, so we'd pull the 2 out front, times 3x squared. Notice the inside, remember, stays the same. We drop our exponent down. So that's the derivative of the outside. Then we have to multiply this by what? The derivative of the inside of the function. So the derivative of the inside, 3x squared plus 4, would be 6x. So to relate that to our problem here with the y squared, think of the 3x squared plus 4 as being your y, and that is y squared, so the derivative would be 2 times y, the 3x squared plus 4, and the derivative of the inside is 6x, which would be the y prime. So in our example, we don't know that y is 3x squared plus 4. All we know is down here, we need to take the derivative of y. So that's why we multiply by y prime. So once again, if the variable here does not match up, in the case we're taking the derivative with respect to the x, we have a y squared, we have to apply this chain rule property, so we get 2y, and then the derivative of y would be times y prime. All right, here we have actually a list of some guidelines to help you with implicit differentiation. Step number 1 says we want to differentiate both sides of the equation with respect to x. Okay, step 2 says we're going to move all the terms involving dy dx to one side and move all the other terms to the other side of the equation. Step 3, factor out dy dx. And then step 4, we want to solve for dy dx. And keep in mind here, dy dx, to make it the notation a little bit easier, instead of writing dy dx, we're just going to simply write y prime. So number 1 says we want to take the derivative, both sides, with respect to x. So here we have our example. Find dy dx, x squared plus 3y to the 4th plus 6 equals 2x to the 4th minus y squared. And let's see, I think I left it. This should be actually a negative 2x to the 4th minus y squared. So if we take the derivative for step number 1, we take the derivative of both sides. We would say d dx of x squared plus 3y to the 4th plus 6, and the derivative of the right side. And again, we're taking the derivative with respect to x. So if we look here, this is our variable. Here the variable matches up. So we simply take the derivative of x squared is 2x. But then we have a y to the 4th. So that means when we take the derivative of the y here, this would be 12y cubed. And then what's the chain rule says? We have to take the derivative of the y, so that would simply be y prime. And of course, the derivative of 6 would simply be 0. And then we again over here have negative 2x to the fourth. Again, the x matches up with the variable here, so the derivative would simply be a negative 8x cubed. Our next term is y squared. Again, the variable doesn't match, so when we take the derivative, we get a negative 2y, and then the derivative of the inside of the derivative of the y would be y prime. Okay, so there is step number 1. Step number 2 says we need to move all the terms involving dy dx, or in our case, all the terms that have a y prime, to one side of the equation, and we want to move all the other terms to the other side. So we already have a 12y cubed, y prime. We want to move over the negative 2y, y prime, so that becomes a positive 2y, y prime, and subtract the 2x to the other side. And then for step number 3, we want to factor out the dy dx, which would be our y prime. So that's the reason we want to, here in step number 2, the reason we want to get the y primes on one side of the equation is so that for step number 3, we can actually factor out the y prime. So we'll be left with 12y cubed plus 2y. And now for step number 4, this is the easy part. How do you solve for dy dx? How do we solve for our y prime? We simply divide everything else away. Since this is multiplication, then we divide, so we end up with negative 2x minus 8x cubed. And this is all divided by the 12y cubed plus 2y. And this here is our derivative. Now, if you notice here, with the derivative, what's a little different from what we've had before is now the derivative here is not only in terms of the variable x, but it's also in terms of y. So our derivative is in terms of x and y. So what that means, if we want to evaluate the derivative at some point, now we need to know not only the x, but we also need to know the corresponding y value. All right, so if we review quickly here, just remember, if your term that you're taking the derivative of involves only an x, and that's with respect to the variable x, your differentiation is just going to be normal, what you've always done. But if you involve a y, if you're taking the derivative with respect to x and you have a term that contains a y, then you must use the chain rule to take the derivative here implicitly.